What is probability? Probability is the likelihood of a particular outcome happening out of all possible outcomes. It's simply equal to the proportion of that particular outcome out of all possible outcomes, or equivalently the fraction of that outcome over all possible outcomes. It could be expressed as a fraction, a decimal, or percentage. Here's a simple example. You randomly draw a marble from a jar that has 10 marbles. Assuming that every marble has an equal chance of being drawn, P of x, which means the probability of drawing any one particular marble I call x out of the jar, is 1 over 10, which is 0.1 or 10%. Let's say 3 are red and 7 are white. Then P of R, which means the probability of drawing a red marble, is 3 out of 10. It's really that simple. There are 6 rules of probability. The first 3 are pretty simple and obvious. The first rule says that every probability is between 0 and 1, or between 0 and 100%. So there are no negative probabilities, that doesn't make any sense, and there are no probabilities greater than 1. That also doesn't make any sense. The second rule says that the probabilities of all outcomes combined, in other words, the probability that the outcome will be any one of all the possible outcomes, is 1 or 100%. For example, if you roll a die, the probability of the die falling on either 1 or 2 or 3 or 4 or 5 or 6 is equal to 1 or 100%. The third rule says that P of A plus P of not A is equal to 1. Because not A means everything that's not A. So the probability of A and the probability of not A includes all possible outcomes. Equivalently, the third rule says P of not A is equal to 1 minus probability of A, which means the probability that the outcome will be any of the possible outcomes except for A is equal to 1 minus probability of A. For example, if you roll a die, the probability of the die falling on any particular number between 1 and 6 is 1 over 6. So what is the probability of it not falling on a 4? The answer is 1 minus 1 over 6 equals 5 over 6. The fourth rule is the addition rule, and it tells you how to calculate the probability of either event A or event B happening. This symbol means union, and it refers to the combination of both these circles in a Venn diagram. In terms of probability, it means A or B. This symbol, this upside down U, means intersection, which is this part where the two circles overlap. In other words, where both A and B happen together. So this means A and B. So the rule says the probability of A or B is equal to probability of A plus the probability of B minus probability of A and B. For example, in this Venn diagram, the left circle shows the percentage of the people who like apples, which is together 48%. The right circle shows the percentage of the people who like bananas, which together is 60%. And the green overlap of the two circles shows the people who like both. And outside the circles shows the people who like neither, which is 32%. The sum of all these values is 100%, as we saw in rule number 2. You can think of these percentages as probabilities of what a randomly chosen person of this imaginary population will like, or you could think of these percentages as actual proportions of the people in this population. They both mean the same thing because probability is equal to proportion. So what percent of people like apples or bananas? If you have this Venn diagram, you can get the answer by simply adding up these three values. 8% who like only apples, 40% who like both, 20% who like only bananas, equals 68%. Or, because the people who like either apples or bananas is equal to everyone minus those who like neither, which is 32%, you can just subtract 32% from 100% to get the same answer, 68%. But if we don't have the Venn diagram, and you don't have these three values, 8% who like only apples, 20% who like only bananas, 32% like neither, all you have of these three values, 48% who like apples, 60% who like bananas, 40% who like both. How do you calculate the probability of liking apples or bananas? That's when you need the addition rule. The addition rule says to get the probability of A or B, add the probability of A and the probability of B. That's 48% plus 60%. Then subtract the probability of both together, because otherwise the overlapping part would get counted twice. Because 48% is 40 plus 8, and 60% is 40 plus 20. So when you're adding 48 plus 60, you're adding 8 plus 40 plus 40 plus 20. So you're counting 40 twice. So that's why you add 48 and 60 and then subtract 40, and you get this probability of the people who like either apples or bananas. Here's another example. You roll a die. What's the probability of getting either 1 or 2? P of A or B is equal to P of A plus P of B minus P of A and B. The probability of drawing a 1 is 1 over 6. Probability of drawing a 2 is 1 over 6. What's the probability of drawing both a 1 and a 2? Clearly it's 0. You can't get two numbers together when you roll a die. Here's a Venn diagram. This is probability of getting a 1. It's 1 over 6, which is 16.67%. Same for probability of rolling a 2. Outside are the probabilities of getting all the other numbers, which altogether adds up to 100%. And you see there's no overlap, because you can't have a 1 and a 2. So to get the probability of rolling a 1 or 2, you add 1 over 6 plus 1 over 6 minus 0 equals 2 over 6, which is 1/3. So we see from this example that if A and B are mutually exclusive, like in this case where there's no overlap, this last part falls out because it's equal to 0. So the rule simplifies to P of A or B equals P of A plus P of B. What if you have more than one or? Like in this example, what's the probability of rolling a 1 or 2 or 3 or 4 or 5? Since they're mutually exclusive, we just add up all the probabilities. Each one is equal to 1 over 6. So the probability of getting a 1 or 2 or 3 or 4 or 5 is equal to 1 over 6 plus 1 over 6 plus 1 over 6 5 times equals 5 over 6. This is the same answer we got a different way in rule number 3. The probability of a 1 or 2 or 3 or 4 or 5 is the same as the probability of not a 6. So it's easier to just subtract the probability of getting a 6 from the total probability, like we did in rule number 3. What about the probability of getting a 1 or 2 or 3 or 4 or 5 or 6? That will be 1 over 6 plus 1 over 6 plus 1 over 6, 6 times, equals 6 over 6 equals 1. And that's just like we derived in rule number 2. Because it's the probability of all outcomes combined, and it is equal to 1. But the reason it's equal to 1 when you add up all the probabilities is because all these outcomes are mutually exclusive. So if the sum of the probabilities of two possible outcomes A and B is greater than 1, like in the example of the apples and bananas where the probability of A is 48% and the probability of B is 60%, then you know there must be overlap, because the total probability can't be greater than 1. So you know they cannot be mutually exclusive. The fifth rule is the multiplication rule, or the joint probability rule, and it's for the probability of A and B. We already saw that this symbol means and. This bar symbol means given that. And this means the probability of B given A. And this type of probability is called conditional probability. In our example, the probability of B given A means the probability of liking bananas given that you like apples. So you focus only on this left circle. Those are the people who like apples. So the probability of B given A is 40% out of 48%, which is equal to 5 over 6, or 83%. What about the probability of A given B? That's the probability of liking apples given that you like bananas. So you focus only on the right circle, the people who like bananas, and out of 60% who like bananas, 40% also like apples. So P of A given B is 40 out of 60, which is equal to 2 over 3, or 67%. So the rule says the probability of A and B is equal to the probability of A times probability of B given A, and it's also equal to the probability of B times probability of A given B. In other words, it doesn't matter if you swap A and B, it will still be the same. In our example, it's saying the probability of A and B, which we know is 40%, is equal to the probability of A, which is 48%, times probability of B given A, which we just saw is 83%. And it's also equal to the probability of B, which is 60%, times the probability of A given B, which is 67%. When you realize that the probability of B given A is just probability of A and B out of the probability of A, and the probability of A given B is just probability of A and B out of the probability of B, then this rule is really obvious. It's obvious that probability of A and B is equal to the probability of A and B divided by the probability of A times probability of A. And likewise, it's equal to the probability of A and B divided by the probability of B times the probability of B. Or in terms of our example, it's obvious that 40 is equal to 40 over 48 times 48. And it's also equal to 40 divided by 60 times 60. So if you have this Venn diagram, you obviously wouldn't need this rule. The rule is only useful when all you have is the probability of A and the probability of B given A, or the probability of B and the probability of A given B. So intuitively, what this rule is telling you is that probability of liking apples and bananas is equal to the proportion of the people who like apples times the proportion of those who also like bananas within the population of the people who like apples. And the probability of liking apples and bananas is also equal to the proportion of the people who like bananas times the proportion of the people who like apples within that population of the people who like bananas. The fact that P of A given B, which is 67%, is not the same as just plain P of A, which is 48%, and likewise P of B given A, which is 83%, is not the same as just plain P of B, which is 60%, tells you that liking apples and liking bananas is not independent. Knowing that someone from this imaginary population likes apples tells you that they have a higher chance of liking bananas, and vice versa. Obviously, this is not always the case for any two variables. Not all variables are dependent on one another. If A and B are independent, then A has no effect on B. So P of B given A, the conditional probability of B given A, is equal to just plain the probability of B. So in such cases, the formula simplifies to P of A and B equals P of A times P of B. You could ignore the part about A because it doesn't make any difference. B doesn't depend on A. And it's obviously also equal to P of B times P of A. Again, you're ignoring the given B because A doesn't depend on B. P of A times P of B is obviously the same as P of B times P of A. This just becomes a simple rule that order doesn't matter in multiplication. Don't confuse independent with mutually exclusive that we mentioned in rule number 4. Mutually exclusive is almost the opposite of independent. It's very dependent. If A and B are mutually exclusive, P of B given A is 0. So what's an example where A and B are independent? Let's say you flip 2 coins. What's the probability of getting heads on the first coin and heads on the second coin? Clearly, these are independent. What I get on one coin has no effect on the other. Each flip has a 50-50 chance of heads or tails. Here's a Venn diagram. The probability of getting heads on the first coin is total 50%. Probability of getting heads on the second coin is 50%. Probability of getting tails on the first coin is everything outside of the circle, which is 50%. Probability of getting tails on the second coin is everything outside of this circle, which is 50%. And here you can see each of the simple probabilities marked separately. Heads on the first, H1, heads on the second, H2, tails on the first, T1, which means not H1, and tails on the second, T2, which means not H2. What's the probability of heads on both? That's H1 and H2. So that's the area that's shaded in both H1 and H2, which is this. H1 and T2 is the area where both H1 and T2 are shaded, which is this. T1 and H2 is the area where both T1 and H2 are shaded, which is this. And T1 and T2 is the area where T1 and T2 are shaded, which is this. So you can see that each of the four joint or AND probabilities is 25%. What's the probability of H1 or H2? That's the part where either H1 or H2 is shaded, which is this. H1 or T2 is the part where either H1 or T2 is shaded, which is this. T1 or H2 is the part where either T1 or H2 is shaded, which is this. And T1 or T2 is the part where either T1 or T2 is shaded, which is this. All these probabilities have three shaded areas of 25% each, so they're equal to 75%. Or if you use rule number 4, you would get this answer by adding 50% plus 50% minus 25%. What's the probability of getting heads on the second coin given that you got heads on the first coin? So you focus on the first coin, H1, and the probability of getting heads on the second coin given that you got heads on the first coin is this part, which is also H2, out of the entire H1. So it's 25% out of 50%. Tails on the second given heads on the first means not H2 out of H1. So you still focus on H1, but take the probability of what's outside H2, which again is 25% out of 50%. Heads on the first given heads on the second. You focus on the second, and H1 given H2 is the part which is also H1 out of the entire H2. And this is not H1 given H2. This is H1 given not H2. And this is not H1 given not H2. This is H2 given not H1. And this is not H2 given not H1. You focus on what's outside H1, which means tails on the first. And the probability of tails on the second given tails on the first is what's outside both divided by everything that's outside H1. So in all 8 cases, the conditional probabilities are equal to 25% out of 50%, which is equal to 50%, just like the simple probabilities. Just as you would expect from independent events, where P of B given A is equal to P of B. And similarly, P of B given not A is also equal to P of B, because whatever happens to A has no effect on B. And likewise, P of A given B and P of A given not B are both equal to simply P of A, because whatever happens to B has no effect on A. So because the two coins are independent, we could use the simplified form of rule number 5. P of A and B equals P of A times P of B. So if you didn't have the Venn diagram and wanted to know the probability of heads on the first and heads on the second, you would simply multiply the probability of heads on the first times the probability of heads on the second. A half times a half equals a quarter. And it's the same for all the other three possibilities, like heads on the first and tails on the second. In all four cases, it will be a half times a half equals a quarter. In this case, you can arrive at this answer by realizing that there are a total of four mutually exclusive possibilities that are equally likely. Heads, 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 tails, tails, heads, and tails, tails. So any one of these four is going to be 1 out of 4. But here's a different example of independent events where you couldn't do that in your head without rule number 5. You flip a coin and roll a die. What's the probability of heads on the coin and rolling a 5 on the die? These are obviously independent events, because whatever I get on the die is not going to have any effect on the coin and vice versa. So to get the probability of a heads and a 5, you just do the probability of getting a heads, which is a half, probability of getting a 5, which is 1/6. So you multiply a half times 6 is equal to 1 over 12, or 8.3%. How can you determine whether two events A and B are independent? Here are the 5 ways to check that we mentioned, and this looks more complicated than it is. The first 4 are just saying that if A and B are independent, all that matters is P of A equals P of A. And it doesn't matter what, if anything, it says afterward about B, because A doesn't depend on B. P of A equals P of A. P of A equals P of A. And likewise, P of B equals P of B. And it doesn't matter what, if anything, it says afterwards about A, because B doesn't depend on A. The fifth way to check is what we just saw, that if A and B are independent, then P of A and B is equal to P of A times P of B. So for example, here, if you did P of A times P of B, that would be 48% times 60%. You would not get 40%. So because we know that the overlap of P of A and B is 40%, and it's not equal to 48 times 60, that's one way of knowing that A and B are not independent. If any of these 5 are true, all are true, and A and B are independent. And if any of these 5 are false, then all are false, and A and B are dependent. You can't have one-way independence. If A is dependent on B, then B is dependent on A, and vice versa. To summarize rules 4 and 5, OR corresponds to addition. To find the probability of A or B, you add probability of A and the probability of B, but this simple addition only works for mutually exclusive events. In general, you must also subtract the overlap to avoid double counting. Conversely, AND does not correspond to addition, as the word AND might mislead you to think. Rather, for probabilities, AND corresponds to multiplication. To find the probability of A and B, you multiply P of A times P of B, but this simple multiplication only applies to independent events. In general, you need to use conditional probabilities to account for dependencies. Finally, we get to the 6th rule, and it's the rule about conditional probabilities. And the good news is we already covered it. How do we calculate conditional probability? We said to get the probability of B given A, we focus on the left circle, and we take the probability of the overlap out of the entire circle, 40 out of 48. That's exactly what the 6th rule says. P of B given A equals P of A and B, which is this, over P of A, which is this whole thing. This rule can actually be derived with simple algebra from the 5th rule. If you solve for P of B given A, how do you do this? You divide both sides by P of A. So you get P of B given A equals P of A and B divided by P of A. So I have a question. Aren't these rules circular? To get P of A or B, you need P of A and B. To get P of A and B, you need P of A given B. To get P of A given B, you again need P of A and B. So it just keeps going round and around. The answer is, of course, if all you have is P of A and P of B and nothing else, you can't get any of these other probabilities. The rules are just showing the relationships between different probabilities. If you happen to know one of these other probabilities, how you could derive different ones. And obviously rules 5 and 6 are going to be circular, because they're just the same equation arranged algebraically, like we just showed. Okay, so we're done with the 6 rules. Let's do an example. Out of all candidates rejected from a job, let's call those rejected due to inexperience I, and those rejected due to failing the assessment test F. Probability of I is 0.6, probability of F is 0.5. The question is, are these two reasons for rejection mutually exclusive? In other words, could you be rejected for more than one reason? The answer is no, I and F cannot be mutually exclusive. If I and F were mutually exclusive, then according to the simplified form of rule number 4 for mutually exclusive events, P of I or F would equal P of I plus P of F, which is 0.6 plus 0.5, which is equal to 1.1. But probability cannot be more than 1, as we saw in rule number 1. So I and F cannot be mutually exclusive. Some candidates must have been rejected for more than one reason. What if P of I and F is equal to 0.3? Then what is the probability that a candidate was rejected for either of the two reasons? And another question, are there any other reasons a candidate could be rejected? Pause the video and calculate the answer to the first question. Rule number 4 says P of I or F is equal to P of I plus P of F minus P of I and F. So when you do the calculation, you get 0.8. So the answer to the second question is yes, there must be other reasons, because only 80% of the people rejected were rejected for one of these two reasons. Okay, a Venn diagram is very good for visualizing probabilities, but it requires you to do some addition in your head. If you want the probability of A, you have to add 8% and 40%. If you want the probability of not A, not liking apples, you have to add everything outside of this circle, which is 20% plus 32%. It doesn't have all the values in front of you. You still have to do some work. What if you had an absolute frequency Venn diagram that just showed the number of people that like and don't like apples and bananas, rather than the percentages? Now, if you want percentages or probabilities, you have to first add up all the values in the Venn diagram to get the population size, and then divide each value by the population size to get the proportion of the probabilities. So that's really a lot of work. Your contingency table lays out all the totals in front of you. It gives you the 4 values of the absolute frequency Venn diagram here on the top left. They call it joint frequencies. And then gives you the sums in the margins. So this is a frequency of B. It's a sum of 120 and 60. This is a frequency of not B. This is a frequency of A. This is a frequency of not A. And the bottom right value is a grand total with a population size. It's equal to both the total of the column, 180 plus 120 is 300, and the total of the row, 144 plus 156 is 300. If you have a contingency table, you don't need any rules to calculate any kind of probability. You can get everything straight out of the contingency table. To get the simple marginal probabilities, you divide the marginal frequencies by the bottom right value. So if I want the probability of A, I just take the 144, which is the frequency of A, divided by 300, and that's the probability of A. If I want the probability of B, I take, this is B, so I take 180 over 300, that's probability of B. Probability of not A is 156 over 300. Probability of not B is 120 over 300. If I want the joint probabilities, the P of A and B, then I just divide these numbers by 300. Probability of B and A is 120 over 300. Probability of B and not A is 60 over 300. Probability of A and not B is 24 over 300. Probability of not A and not B is 96 over 300. To get the A or B probabilities, you just focus on 3 of these 4 values and always remember to divide by 300. So to get the probability of A or B, that will be these 3 values over 300. So you could either add them or you could get help from one of these 2 margins. So to get 24 plus 120 plus 60, you could just add 180 and 24 or add 144 and 60. And of course divide by 300. If you want the probability of not B or A, would be these 3 values. So you could just add 120 and 120, or you could add 144 plus 96 and then divide by 300. If you want the probability of not A or not B, then it's these 3 numbers. So it's either 156 plus 24 or 120 plus 60, and then divide by 300. To get the conditional probabilities, here is the only case we don't divide by 300. We only focus on the relevant row or column. So to get the probability of B given A, because it's given A, you just focus on this column. So B given A is 120 out of 144. Probability of A given B is 120 out of 180. Probability of not A given B is 60 out of 180. Probability of not A given not B is given not B is this row. Not A given not B is 96 over 120. Probability of A given not B is 24 out of 120. If you divide all these values by this value here, then this value will become a 1 or 100%. And all these other values will turn into probabilities. And then this table will be called a joint probability table, which will give you the probabilities directly. You won't have to divide by this grand total.